So it says introduction, but it's really an introduction how to use the system. And tomorrow at the same time I will explain how it's implemented. So Andre said, okay, my work group is how to implement a proof assistant. Well, I will tell you how HOL is implemented. So that's another example of that. Okay, so like I said on Monday, the hardest part of HOL is how to install it. And here is the one slide summary of it. With James we did it and it almost worked. So I mailed John about it like it didn't work, and then by now I thought it would be okay. So maybe we should figure out exactly what went wrong there. But if you install it, then you're past that hurdle and there's no problem anymore. So how do you do it? You go to this Git hub repository and you clone it, and then you have all the files, and it's really small because it's just source for the source. There are no bindings or anything. And there's a README that's very extensive. John is a very good writer and he has lots of documentation and stuff. So this README explains lots of things. So basically what I say here should be in the README. And then you need to install a compiler for OCaml and a front-end for OCaml called OCaml P5. And the reason for this is that HOL is a clone of the original HOL system, and the original HOL system is all capitals. I also talked to Andre about this in the during coffee, and John wanted to clone this. But in OCaml, everything needs to start with lowercase. So that doesn't work. So he hacked the system. This OCaml P5, he doesn't even use it in the way it's supposed to be used. He replaced one source file and he mangles it so that the capitalization of OCaml is not there anymore. And that makes life interesting. So there are different ways to do this. If you're in Debian and you just install OCaml and OCaml 5, it doesn't work. I tried. You can, because basically the versions need to match to have this hack work. So what you can do is install it from sources. I think that's what John does himself. But you also can install some monstrosity called OPAM. I probably offend some OCaml people now, but I really dislike OPAM. And then you can have a switch for different OCaml versions, and here is the little script that installs two versions. I don't know whether these numbers are the best choice. It didn't work on numbers, so maybe it should be different numbers. And you need to install a library called num for big numbers and things. And then what you need to do is this patch file, so pa.ml is part of OCaml P5. He has made his own version PAJ for John. And there's makefile, and so if you say make, then there's about 1,000 copies of this for all kinds of versions. It takes the right one and compiles it, hopefully. So good luck means that it's an interesting experience. Okay, so then what do? The makefile produces also a hol.sh, that's a script that does the right things. But what you also can do is just run OCaml. It's nice to have some Let or rlrep in front, so you can go back to previous things and edit your history. And you need some include directories and some binary for the OCaml P5. So this magic command loads the right stuff. And what you do then is you're in an OCaml interpreter and you can just type OCaml commands with some stuff loaded. And then what you do is you say use HOL ML, and HOL ML is the top level file in the source directory. Source directory is extremely simple. There is a HOL.ml and a bunch of other files, and HOL.ml said load all the other files. So they get processed one by one, and while processing it, all the things it's compiling, how do you say this, loading are printed, so you have 20,000 lines, that takes about 1 minute, and then your basic library is loaded. And you need to do it every time you start the system. The system is extremely primitive. Basically, when starting the system, you need to wait for 1 minute. That's not completely true. There's something called checkpointing, where you take the Unix process and then you say from the outside, okay, dump this process on a file, and then you can reload that file and the process continues. But that also depends on the version of Linux. The newer Linuxes have security behaviors that make it not work anymore. So I think John works, uses an old Linux in a virtual machine. It's all a bit hacky, but you also can just wait for it. Okay, this is clear, I hope. So, then you're in an OCaml interpreter, so this is fake. I could type C++, but I just put it on the slide. You can type OCaml expressions. I don't know whether you've ever used the interpreter for functional language. Yeah, and OCaml, there are lots of people who are fans of OCaml, so they will be happy to be able to type OCaml expressions, and it gives you 7. That's what it should give you. Okay, and then you can also write C++ in backquotes. So these are not single quotes, they're, yeah, I don't know how they're like this, right? And what that does is it gives you a whole term. So this is not a number, it's a data structure that represents something in the logic. Okay, and it says term, and the pretty printer prints this data structure back in backquotes also, so you can easily copy paste. Well, now we have 2 copies of C++, one as a number and one as a term. Basically, there is this OCaml level and there is HOL level, and we have C++ on both levels. This backquotes is just a hack in this PAJ thing. You can also do, it basically calls the function parse term. So parse term is a function that takes a string and returns this term data structure, it parses it. This is exactly the same. These backquotes is just so you don't have to type parse term. Okay. Then you can take this term and give it to a function. So all you're doing when using HOLite is calling functions that you have been loading at the start of the session. So one of the functions that's defined is called typeof. It takes a term and it returns a whole type, and the whole type is num. Normal people call it not. It's natural numbers, but the whole culture is to call it number. Okay, you would expect the type of it to be type, but type already is an OCaml keyword, so it's called whole type. Okay. So you can also type num in backquotes with a colon in front, and then it gets parsed as a type instead of a term. So the convention is if a backquoted expression starts with a colon, it's not a term, it's a type. The type parser is used. Okay, so we have 2 data structures for terms and for types. That's nice. And then you can say, okay, but who cares for C++? I want to know the answer. So I want to compute it. And here we are a difference between the whole systems like Isabel and HOL 4 and HOLite on the one hand, and the type theoretical systems like Agda and Kok and Lean on the other side. In Agda, Kok and Lean there's a notion of computation. That's hardwired into the logic. That's what makes the logic big. It's what makes the kernel big or slow. Your choice if you want to make it fast, you make it bigger, because there's an evaluator in your logic, there's an evaluator in your... In the whole systems, tomorrow I'll explain the logic, there's nothing like that. It's extremely simple, which means that to compute something, you need to run a program. And the program in this case is called numReduceConf. So conf is called a conversion, and what it does is it not only computes it, it proves it. So the input is the term C++, and the result is not the number 7, but a proof that C++ is equal to 7. So that's the definition of a conversion in the whole world. It takes a term and returns a theorem, which is an equality with the term that you gave as the input on the left-hand side. And because there can be different conversions, there are different notions of computation. In type 3, I'm stuck with the one notion of computation that the logic calls state. In HOL, you can have many conversions. So in type theory, dependent type theory, there are 2 kinds of natural numbers. There are the binary natural numbers, and they're efficient. There are the unary natural numbers, and they are good for induction. And you can convert back and forth. And if your James McKenna is called view from the left, and then you can do interesting signs. But you have these 2 definitions, and they're not the same, because the inbuilt reduction is not the same. In HOL, you don't have that. Is this binary? Is this unary? It doesn't make any difference. You have binary terms, you have unary terms for it, and you can have these conversions, manipulate these terms. So it's a really different mindset here, and more flexible. On the other hand, this really is doing a proof. It really goes to the kernel. That makes it slower. Okay, and then you can say, I don't want the theorem, I want the number. So you can take this thing, so this if thing is not part of a camel, that's part of the hack that John put on top of it, and that's from the original whole culture. Everything you evaluate is stored in a variable it. So instead of saying this expression again, you can refer to this thing. You take the conclusion of it, that's this term c plus 4 is 7, and then there's a function right hand side, which gives you the right hand side. And then you have your 7 as a term.
Okay, so does HOL have like exclusively definitional or also propositional equality? How do I think about that?
Okay, that's a very good question. I didn't prepare for that, but okay. In type theory, you have bool and prop. And you have three kinds of equality. There is the equality that returns bool, the decidable equality, is the propositional equality, Leibniz equality, or whatever you call it, book equality, it was called in the Automat days. And then you have convertibility, which is not something you can write down, it's from the meta level, right? So there are lots of equalities, lots of truth values. In HOL, there's just bool. Bool is used because it's a classical system. Bool is used for this term here, c plus 4 is 7, the compound of its, that's type bool. And there's just equality on any, just A arrow bool, that's the type of the equality. And there's no convertibility because there's no computation. And the nice thing is, so in Cambridge they have a system, I forgot the name, that's supposed to be able to output Isabel and Coq and OCaml, and you have basically in the other data types and recursive functions and inductive predicates and stuff like this. And you can work with all these systems together. And we had a semantics for the C language that we tried to put there. One of our students wrote his master's thesis about it. And then that was made by HOL people. And they don't understand the difference between bool and prop. It didn't work. Some things needed to be in prop, others in bool, and the system could make the difference in some way, but not in the way that it was useful. So they really got confused because in their world it's the same thing.
So like a classical example is if n and m are natural numbers, then n plus m equals m plus n, but it's definitely not definitional. So
there's no definitional equality here.
Oh, but there could be a proof that n plus m equals m plus n, and
of course there is.
You wouldn't store that proof.
Yeah, no, you don't store any proofs. This is ephemeral proofs. Once I have this, if I will ask, what was the proof of this? Then we use conf did a proof. The C washed it away. It went through the kernel, it's gone. The only thing that's remembered is the term. And maybe some good conditions here if these are sequence. So,
can there be variables on the left-hand side of the sequence?
Yeah, sure. There's no context for variables. The variables are free like in ordinary logic. Okay, so let's make, okay, and then you can look at numReduce conf, because the function language, you not only can call it, but you can just look at an object and it tells you it's a term tool still. And this is, it has a name conf, this is the type of conversions. Okay, so there are two kinds of typing here. You type it in OCaml and you have typing in HOL. So here are the three main OCaml types that corresponds to stuff in HOL. You have term, type, and theorem, and unfortunately it's HOL type. It would be nicer to have it be called type. So those are the three data structures that represent the mathematical objects, the types, the theorems in the system. And like I said, the theorem doesn't encode any proof. It just remembers that the thing has been proved. And I'll explain tomorrow exactly how you know that you cannot fake that, how that works. Okay, but so there is some duplication here. We have the term c plus 4 and the term, we have the value c plus 4 and the term c plus 4. We have the OCaml type int and the HOL type num. They're not the same because int is integers and num is natural numbers, but they're kind of similar in the sense that they're the type of c plus 4. And this duplication, you get everything, everywhere. So you have these two layers, and so that might get confusing. So we have true and bool, false as OCaml values. We have t and f as HOL, true and false, and we have bool on both levels. That t and f are constants is really inconvenient because you cannot use them as variables anymore. It's similar to O and I in Coq a little bit. I mean, O is to the 0 and I is to the proof of true. Well, why people would use one letter things for that kind of thing, I don't know. And then we have the same things with typing in HOL. So 3+4 on the camel level is a term data structure, but in HOL, in the whole logic, it's typed as a natural number and true and false are typed. So this type thing here is on a difference in the logic. Is this clear? Okay. So now I made a dictionary of whole syntax. I went through a couple of examples, and so these things might be useful. So we have NZ, R, and C. I don't know where there's a Q. I didn't remember to look. Probably there's a Q as well. Num, int, real, complex. So complex is not loaded standard. For that you need to load an extra set of files. Booleans, unit type, Cartesian product, disjoint union or co-product. I learned yesterday it's called option type, lists, functions, what you would expect. Sets, we're type theory here, we have types and sets. Types are disjoint things. So int and num and real, they don't have anything to do with each other. If you want something like sets that can have an intersection or union, you basically code it as a predicate on a type. So basically the sets are subsets of a type. In a more advanced system, there would be a thing like set for it, and John is the bare bones type. So he just writes A or bool, that's what it is. Okay. And then there is a very funny thing for Cartesian products. And this is basically a dimensional vector space. So they're vectors. If you depend on type theory, you call it vectors. Okay. Everyone knows you want dependent types for this. But we don't have dependent types. So he's faking it. So these A, B, and so on, they're type variables. You can put any type there. And this N is also a type variable. You can put any type there as well. So you can say, for instance, real numbers, real, het, real. What does that mean? So he's using types to code natural numbers. And it's really a hack. And some people like it, and some people say, this is really strange. So types can be used to encode positive natural numbers. So if the type is finite, it encodes this number of elements. If it's infinite, then it encodes the number 1. So if I do real, het, real, that really is a type that's a one-dimensional real vector space. That's weird, right? So the parser knows this. If you put a number here, it will generate for you a type with that many elements. And that's why I made the one red there. That's the one of types. You have computation of types, and it's weird, but it's also kind of makes it, yeah, kind of nice. I said positive natural numbers here, so I probably will offend you won't see this coming. Holite doesn't have empty types. And if you're a very Howard person, that's crazy. That's really crazy. Also, if you're a mathematician, that's really crazy. Mizar doesn't have empty types, and that's the reason I left the system. Some types are naturally empty, but they don't think it's possible to have empty types because they don't understand things enough. HOL has, for various technical reasons that are probably better, no empty types. So, well, there's no 0 here. Okay. And the reason I think to not have empty types is you want a choice operator. And the choice operator always needs space to return something. So, yeah, if your type is empty, what is it going to return? And, okay, let me take back that it's crazy not to have empty. If you have dependent types, then not having empty types is crazy. These are not dependent types, so then it doesn't matter so much. Okay, the same thing for terms. I recently learned that the number 1728 is quite nice, so I used that as an example, the J of I. So, like in all these systems, you have a different version for every type. So if you just put it, it's a num, it's a natural number. If you want it as an integer and a real, then you put an ampersand in front. And the question is, which one do you get? And the answer is, well, it depends. So the type is there's type inference that tries to get the types right. If from the type inference it can decide which ampersand to take, it takes that one. If there's no type inference, if I just type this term, then there is something that gets the priority. So there are functions prioritize int, prioritize real, prioritize something else, I don't know how many there are, and you can call them and then you get one of the two. And for some reason, for complex, it works differently. There's a function cx that maps a real number into the complex number. Okay, complex number I is called I, not I of j, like Michael was saying yesterday with I, real part, imaginary part, the various arithmetic stuff. These things are overloaded. Like I said, the parser is extremely simple. There are two things. There are numerals, you see them, 17 and 28, and there are overloaded operators. So depending on the types of x and y, you get different minuses. Yeah, different modes. We have x and power. I never know which one is which. I always have to try. The square root, arbitrary roots, if then else. In Isabel you need to put brackets, but this is not Isabel. The element of the unit type, when I was making this list, I went through my list of types. Okay, what are the operations for these types? I got to the unit type, okay, the inhabitant, which I made, Andre made a dot yesterday. It's called 1. Pairs, projections, in left and right, all the stuff you would expect. More, none and sum. I said the parser is extremely simple, but it knows about lists, so it's not that simple. It also knows about subsets. So there is some parser magic. Then I don't know how many people know Latin calculus here. So mathematicians write it as the funny arrow. Computer scientists write, or logicians write it as lambda. The lambda is the backslash. Okay. Function applications is functional programming language style, so you don't put brackets for comma, you just, all these things have curly types. Subsets, I already talked about the sets. Notion of being finite, that's a property not of a type, but of a subset. Oh, I forgot to put unif. Unif is the whole type as a set. I should have put it. Cardinality, subsets given by predicate, a range from n to n as a set. Okay, then we have these vectors, so you can convert a list to a vector, a list of function vector. To index a vector, you use $. Okay, so we have sum, and there are two versions of sum, so we don't have typecast or anything. And sum, the things you're summing are natural numbers. Normal sum, the things you're summing are real numbers, and the same for products. And then you can sum over an arbitrary set, so this n.m I just showed you is just a set from n to n, so if you have a different set, that works also. And then the rest is kind of strange. And we saw that on Monday with Isabel. You don't write the integral of something, or the sum of an infinite sum or something, because it doesn't need to exist. So what you use is a relational style. You say, this thing happens to sum to this value, but it's not a term that you can use as a sub-expression. You can have this, but then it gets strange values in case the thing doesn't converge or doesn't exist. So, because the logic is total, every expression has some value, which you might not be able to say anything about. So, infinite sums, limits, derivatives, integrals, they're all written relationally. So in PVS you don't need to do this, so that's why we did it. Okay, then how do you write formulas? That's kind of what you expect. So for all is exclamation mark, exists question mark. What is important is the operator parser is extremely stupid. So the not P, which I put there because I like intuitionism and it's clearly something different from P. You don't put the nots together. because then it parses as one operator, not. And that always bites you. If you have the not of for all, then you need to put brackets or space and everything like this. Okay, so the for all that exists have variables and also free variables in terms. Generally, you don't tell the system what the type is. It looks what you do with it, what functions you apply, what predicates you put on it, and from that it infers what the type of the variable should be. Called Hindley-Milner type inference, and that makes life interesting. So suppose you're proving a goal that has a natural number x in it. And then you say it's useful for me to take this x and give it to some conversion or to something like this. And you type backward code x. The parser here doesn't know about the goal. So it just says, oh, there's an x, I don't know what type it should have. There's no function being applied. Let's give it the most general type. It invents some random type for you. And then it doesn't work because it should be so you really should give the type explicitly in the variable then. And okay, for beginners and like me, that's okay. So now I'll show you how to do a proof, and for this I took this proof. At some point in a museum I bought 5 balls with proofs on the infinity of primes and Pythagoras and so on. It's called the proof of the pudding. So on the fringe there's the statement, and on the bottom there's the proof. So you eat and then you get the proof. And this is one of the 5. So let's do this one. And this is one of the top 100 ones as well. So it was the shortest one in the top 100 list. There's 100 directory with all those top 100 proofs in it. So okay, let's do this one. And the one that John proved is the general one with arbitrary arithmetic progression. This is the simplified one. If I simplify a statement, I get that. So I could copy that and it would be extremely simple. And it still will be extremely simple what I'll be doing, but it's a little bit less. So the strange thing here is, this is in natural numbers, there's an n sum. And you might expect division by 4 division by 6 to be 2/3, but it happens to be 0, because it's natural number division. And if you do subtraction, there's no subtraction there, but then 4 minus 0, 6 is not minus 2, it's 0, because it's natural number subtraction. That's really making life weird. So I don't like that. So it means that this 2 only gives the right answer if you put brackets around this product. Because n and n plus 1, one of them will be even and then it works out right. If I write n times n plus 1 div 2 without brackets, if the n plus 1 is odd, it gives the wrong answer. So I hate that. Okay? If I put an ampersand here, so I go to the real numbers or integers, then it does the right thing. So I want this statement to do the right thing, so instead of doing an n sum, I'm going to do sum.
I think you could also go a bit more into detail with this n sum and the lambda I, because some people might not see.
Yeah, okay, so yeah, thank you for helping me. It's hard when you're too close. Okay, n sum blah blah blah, that's how you write a sum. And what it means is this lambda IFI at the top, I also had that. That's a function. X arrow from lambda f x of x is the function of x to f(x) of the lambda expression if you know the lambda notation. Okay? So what we're doing here, we're applying a function n sum to 2 arguments. The first argument is a set, the numbers from 1 to n. Second argument is a function on all the natural numbers, not on that set, but on the full natural numbers. Identity function. And of course, together that allows you to write out this sum. Is this what you wanted to do? Okay. So, and as you can see, for the real numbers you need a different reduce call thing. That's a disadvantage. So I think in HOL 4 they have a conversion that's kind of generic. It knows lots of stuff about lots of types, and it's called eval, and it was written, I think, by Bruno Bras. So there was some crossbreeding between the data type theory and HOL.
Is that a minus there?
Yeah, so minus is the infix, minus and minus.
Why does it agree with that?
Once again, go away. Where was my theme? Here. So minus x is minus x.
Okay.
Like I said, the system is not really trying to do its best to be helpful, just enough. And you say, why is
No, I was reading that as minus as opposed
no.
to a single
If you do minus, there needs to be a space in between.
Right.
So the thing I'll be proving for you today is the real number sum, and I need to put ampersands everywhere. So if you're a lean person, you have this funny up arrow everywhere. It's the same thing in Unicode. And in my statement there was no for all n. There's not for all n. So I'm going to prove it without for all n, and that makes life also more interesting. That's basically what makes the script twice as hard work. Right? I decided I want this one because that's what it looks like. Okay, so let's do it. And like I said in the whole session, all you do is call functions. So we're calling a function g with the term, the thing we want to. And the system warns us, are you aware that there's a free n there? Yes, that's what I wanted. I didn't want this for all n. I don't know what the custom is for actual light users, whether they prefer to have this free or with a for all n. And then it says, okay, we have a goal now, one goal, and it prints the goal for you. And this g function, it's just a function. It takes a term, and it's what it does, it sets a variable for the current goal. So OCaml is not a pure functional language. There are states, there are variables that have a value, there's one variable that has the value, this is the goal. It sets that value and then returns the value for convenience so you can see the goal immediately. So all it does is tell you what the goal now is. Okay, and then we're going to execute the tactic. Because the first thing I'm going to do is I'm going to put that for all back. And why do I want that? I want to do induction, and induction wants the for all quantifier at the start. So if I had taken the original one, this whole spec tag wouldn't be there. But I didn't want that in my statement, so I put the spec tag there. What does spec tag do? It takes a free variable n and puts a quantifier in front and uses m for that and substitutes m for all the n's. I don't know what it's called in Coq. I don't know it's called. Someone will tell me. What?
Revert, I guess.
Reverts? Does that also work for variables? Yeah, it probably works. Yeah. Okay, so again, g is a function, e is a function, it executes the state and then returns the state. So this return goal stack it could be units, but then you would need to type what is the goal all the time. So spec tag is a tactic. And that's different also from when you have a real proof language, because as you can see, there is no proof language here. We're just executing OCaml. Spec tag takes two terms as a product, so it's not curried, comma in the middle. And it returns a thing called tactic, which is some kind of function that does stuff to the state. Okay? Okay. And then, like in all systems, eventually, all you need to do to use the system is know what tactics there are. You have this huge list of tactics, right? Okay, so new slide, and I forgot what my goal was. So we have the p function that prints the goal. So this was our goal. We have a for all in front now. This exclamation mark was the for all. And now we're in the induct tactic, and now we have two sub-goals, and it prints it at, well, this is induction. Everyone knows induction. Our first year students find it hard. I don't know why. I really find it hard. Okay, that's nice. And it prints them all in opposite order. So the first, the one that you will work out first is at the bottom, because this is a primitive system, so everything will scroll out of view. But the one you want to work on should be on the bottom, right? Then you can still see it. Okay. So I looked at John's proof, because I didn't invent the proof, the top 100 proof, and he uses something, a theorem called sum clauses numsec. And, well, that's this, if it's 0 is this, it looks like recursive definition of sum. But it isn't, it's not the definition. You can use it to rewrite, but the definition is for arbitrary sets here. This is an instance. So this is, if you're used to recursive functional programming, you say, this is how you define sum, but no. This is just a theorem that you can use to do computation. Okay, well, nice to know that this is useful. So let's rewrite our goal with it. So, what was the goal? Let's remember. The sum from 1 to 0 is 0 times blah. Okay, so if we write it with this, the sum from 1 to 0 is if blah blah. So now we have to go if blah blah is 0 times 0. That's our goal. And now I add a plus in my table for automation. I just say, yeah, this is okay. You can do this yourself. It's not as powerful as grind. But this kind of arithmetic things, including the multiplication and so on, everything else, we'll just do it. So arithstack solves the goal because it's maybe not clear. We had this one subgoal after rewrite tag, so it only prints the thing, the goal that gets generated by the tactic. In the other goal, it says 2 total is not repeated all the time because it gets mixed too clever. But now this goal is gone, and we're back to one subgoal, the induction step. So now that one is proven. So we're basically done with the subproof. Okay. So now, now if I do the rewrite tag sum closest numsec again, which was the one that I used that I took before I went to the real numbers, it doesn't work. If I do rewrite like this, and then arithmetic says, sorry, I cannot do this. Gives an error. And what is really looking fishy to me is this ampersand sub-m. That looks like the sub-m in real numbers, but this sub-m is not about real numbers. So maybe there's a nice lemma to rewrite this. Okay? So now I'm going to show you the search function. There's a search function, and it's inspired on Google search. You can give it terms, and it will try to find theorems that match the terms. You can say name and some string, it will give you theorems that have the string in the name. You can put minus in front of it to suppress stuff and so on. It's quite nice. And it tells you there in basic library 2 lemmas that have sub-n in it. Okay, well this real of numsec looks really useful. Let's see whether that really exists. So real of numsec, yeah, it's a theorem. It says that n plus 1 is ampersand. But it's the wrong direction. So what we're going to do is revert it, and for that we have a function called gsim that takes the theorem and generates a new theorem in the opposite direction. So gsim real of numsec, that's what we need to get rid of those sub-n's, and it will reply to places it goes. Okay, so now we do rewrite tag. Instead of rewrite tag, we do SM rewrite tag, which also will rewrite with the induction hypothesis, which of course it should do. With both the sum clauses numsec and the gsum field numsec. In normal, no, it would be behind it. This is big letters on that.
You've just used it here?
Yeah, I could have replaced gsum real of numsec with it.
Okay.
Yeah, of course. And then I get this horrible thing, but fortunately, Wiedijk can do it now. And we're done. Okay, so this is the interactive way of doing proofs in the system. And then you can call a function top theorem to show that it really proved it. We have a theorem that says, which was my goal. This top theorem you never call, but it is in the system. Okay, so to repeat, this was the steps you went through, and these were the things you used there. You can set a goal, you can execute the tactic, you can print the goal, you can undo the last application of the tactic, and it's multiple undo, it's called back. And this one is not really useful. You can see that from the fact that there's no knowledge. But this is not what you put in your file. What you put in your file is this. So, and as you can see, it proves it. It's exactly the same tactics, but now connected with a keyword then in all capitals. So you do tactic, then, next tactic. But it's in that tag generates 2 subgoals. So you say, okay, then L, we give a list of continuations. The rewrite tag then array tag is for the first subgoal, the rewrite tag then array tag is for the second subgoal. So in the structure of this then and then L and the list there, so OCaml list there is a semicolon for people who don't know that. You see the structure. It's a bit like bullets in Coq, and I don't know how it's in Lean. That's what?
Both.
Also bullets, not just indentation or something.
Just one both.
Just one. So this is the whole light equivalent of that. Not as nice as bullets maybe. And so this example now we can use in our rewrites later. We say a rewrite tag example, and then it will rewrite this sum to this.
Question?
Yeah.
So, suppose I interactively did what you just did.
Yeah. But this is what you put in the file, and then you say
Who
local.
puts this in the file?
Yeah, that's a very good question. So I think John has just a session open, an editor open, has a magic keystroke that copies back things from the editor to the session. I made a VI mode that automates this in VI if you're a Vim user, and it doesn't work anymore. I tried to demo it on Monday, but OCaml changed. They make difference between strings of bytes and strings and binary data. It used to be the same, it's not the same anymore, so my code broke. But I automated this. But like I said, this system doesn't have an interface.
So you're supposed to kind of manually keep a diary, a log of what you're doing.
And if you mess up, you have to restart the interaction.
If you really fuck up the system, yes. I made a version of HOL that can undo definitions. The real HOL cannot do this.
You can
No one
undo
uses it. What?
You can undo E. Right?
You can undo E, yeah, you can just start from new G start again. Yeah, but if you add definitions and you regret that, then you're
But see, if you have proof terms, you can just rewrite parts of the proof term and not a sequential sequence of steps. You can go back and you can edit.
You can regret it. Yeah, sure. I'm not trying to sell the system here, I'm just trying to.
I was rather hoping that there is a meta tactic that secretly reports what you're doing interactively.
Like I said, I made a Vim mode for that.
Yeah.
And it was a very nice Vim mode. I never used it. No one ever used it. I have one user, Dan Bernstein, some crypto specialist from Eindhoven, or he's not in Eindhoven anymore.
50% of Vim users use it.
And he uses only the half of it. I have some nice thing that the goals automatically appear somewhere into general style, and that part he doesn't use. He just uses the communication. He hacks it. Anyway. You can hack this, no one did, I did, but no one uses it, so no one feels the need. This is John Harrison's private vehicle. And some other people use it, but it's mainly his. And he has some workflow with his own editor, and he has a keystroke that puts it in the system.
How did they manage to do the Kepler projector?
Ask Tom Hayes. Ask John. I mean, it's like with MetaMask. MetaMask to me is like a toy for children. And then this guy comes and it's one of the highest ranking systems. People are good. The problem with these systems is not the interface. The problem is finding dilemmas, finding the way around the proof. That's where all the pain is. So this is minor pain on top of that. That's how I experience it. Okay. The proof function takes a term, it takes a tactic, and it returns a zero, not should expect. And then, yeah. 3 minutes! Oh my god! Oh my god! I timed it better this. Last Monday I had much too much, but this is I'm reasonably close to it.
Yeah, good.
Then and then L are combinators, so brackets in OCaml means it's an infix thing. Of course you cannot have that as an infix thing, but that's the hack of the front end again. It turns out if after the then L all the tactics are the same, you can just use then. So if you do tactic 1, then tactic 2, it applies the second one to all the subgoals generated by the first one. And it turns out if you do the SM rewriter, blah blah blah, on the 0 case, it also works. So you can simplify this. So this is actually what would go in the file if I would do this for you. Okay, briefly, what is intro in Go? It's called dish tag. Okay, what is apply? I mean, if you're type space, you want into and apply. Apply is called match and p tag. Okay. Measure p tag is a function that takes a serum and returns a tactic, so. Okay, and it's not as powerful as the real apply, but it's nice. So I felt, okay, slide 19, I'm close to the end now. I can have 20 slides for 40 minutes. So here's just a list for all the natural deduction rules of tag. If you want to know what is split, well, split is anti-introduction, so that's form tag. And then there's strip tag, which basically says, do the reasonable thing. That's a rule in Isabel. And so basically what you do is you do intros at the start, and intros in what's called repeat strip tag. But that's on my t-shirt. Repeat strip tag, and then make love. Okay. Here's some more tactics. So there are rewrite tag, sim tag is conditional rewriting, and then there's mise on tag. So in Isabel it's called Metis, in PDS it's called Grind. In Lean it will be called Duber or something like this. Basically it's first order reasoning. If you have a goal that just needs first order reasoning, mise en tac, and it will finish it. You don't need to think about the natural deduction steps you need to go through. So generally, whole life proofs end with mise en tac. That's close the step. It's a blah blah blah. So the basic structure is do repeat strict tech, do then something like induct, then rewrite a bit, and then do mise en tac. That's all the proofs look like. Okay, how do you find out about things? There are lots of materials. This is one I made. What I did is I grabbed all the sources for all capital identifiers, these statistics, and I got a list of, apparently these are interesting. And John said, oh, this is nice, and he gave one line explanation of all of them. And we had hacked it together, so this is a cheat sheet for all the stuff that you can do. And then there's one more feature, this is the last slide, so please don't rush me. There's a help function. So John has for all the stuff that's in the system, all the tacticals, conversions, everything. A one page, it really looks like Unix one pages. And you get it, you can look in the directory with you, and it's also in the document. You can also inside the system just say help. And so if you say help, help, it will explain you what the help function does. So that's it. See you tomorrow.